Hello, Algebra 1, Lesson 1.4. So today we're going to talk about number sets. Number sets are, remember we talked about in the vocabulary lesson 1, the first lesson of this unit, that humans, we just like to classify stuff. I mean, you study biology, you've got all the different classifications that we put living things into. So we don't stop in science classifying things. We start classifying things when we're a baby. You're taught, to put red items together and blue items together, and not to, you've got the little box with the holes in it to put the circle pieces in the circle holes and the squares in the square holes. We want to classify things. It's natural to us. So we have actually classified numbers, and we talked a little bit about that in the vocabulary lesson 1 video. If you want to go back and look at that, you can for a quick review. But we're going to cover most all of that and more in this video. So the number system that we're going to start with is natural numbers. Now, what natural numbers are is what you naturally would just begin counting with, okay? So when you have 10 things, you start counting 1, 2, 3. And does that ever end? No, it doesn't. It goes on and on forever and ever to infinity. So these ellipses, which is 3 dots, indicate to us that this set will continue on forever in the direction of positive and growing bigger. And if you notice, it goes up by a whole number every time. We don't naturally count 1.2732. We don't naturally include the decimal points. Our natural numbers are just simply counting numbers. Now our next set is whole numbers. The only difference between whole numbers and natural numbers is that it starts with the number 0 and it continues 1, 2, 3, and so on. So all of these numbers are going to be, you guessed it, whole numbers, and they're all either 0, which doesn't have a positive or a negative, and positive. So we've got this whole, which just is what we use to represent nothing, right? This 0 plus all of our positive whole numbers, 1, 2, 3, and so on. Okay, then after that we get integers. Now we did talk about integers a little bit. Integers, remember, continue this process. We have -1, -2, -3, and it keeps going on in this direction. So when we get to integers, if you remember, this is a Venn diagram. You were first introduced to them back in elementary school. They helped you to put your thoughts on paper and see what overlaps and intersects and what's separate. So in this Venn diagram, if you notice, the natural is completely inside the whole. That means that every single natural number is a part of the whole number set. And then every single whole number is inside of the integer set. And so these sets are just building one on top of another. They're just getting bigger and bigger and bigger. And so integers includes all the whole numbers and all the natural numbers plus their opposites. And remember, the opposite of a number is simply its negative. So -1, -2, -3, and so on to infinity. So integers go on to infinity, down into the negative as well as into the positive. So we have ellipses on both sides of our set. If you were to write this in set notation, you'd have the squiggly bar that I don't write very well, and you'd have an ellipses, -3, -2, -1, 0, 1, 2, and some more ellipses and another squiggly bracket, curly bracket, I think is what they're officially called. All right, so after that, we have rational numbers. Now, this is where it starts to get really important. In Algebra 1, you need to know the difference between a rational number and an irrational number. Those are the two main types of classifications we need to be concerned with, okay? Now, a rational number is any number that can be written as a ratio. And a ratio is a fraction of integers. So you're not gonna have it like x over 2. So it's not just any fraction, it's a fraction of integers. So rational number written as a ratio kind of makes sense, right? But another way to think of it is any number whose decimal terminates, which is another way to say ends, or repeats. So in other words, we have the fraction 1/4. That equals 0.25. So it ends. It's also written as a ratio. So this is a rational number. The fraction 1/3 can be written as 0.3 repeating. So that is a rational number because it repeats. This one terminates, this one repeats. But if you see in the Venn diagram, it also includes all the integers, whole numbers, and natural numbers. Because we can take any of these integers and write them as a fraction. Remember, whole numbers, we know, can be written as a fraction simply by putting them over the number 1. Sometimes you even have some numbers, let's say -4/2. That is not in its simplest form. So we could continue to simplify this down to a -2. Okay, so it is still in the integer category, even if it's written as a fraction. Okay. So then we have, after that, real numbers. So you'd be surprised to find out that there's actually a set called imaginary numbers, right? We got creative humans, mathematicians. They're like, oh, that's not possible. But yet it still happens in math. So what do? We create something called an imaginary number to take care of it. And we'll get into those in just a second. But real numbers are any number that's not imaginary, right? Any number that's not imaginary. Okay, so we've got natural, whole, integers, rational, real. So if this is where rational is, then our irrational is going to be this area in the real that's not in the rational area. And I've got a chart to show us that in just a second. But first, I want to get to the fun one. The irrational, imaginary, and complex numbers. Now, we're not going to get too much into these this year, but know that an imaginary number is simply the number I. And that's a symbol, of course, which stands for the square root of -1. Okay, the square root of -1. And complex is a combination of real and imaginary numbers like 3i. Okay, one thing I failed to mention is that rational numbers, besides, okay, well, we didn't get to irrational yet. So we've got natural, whole, integers, rational, imaginary, and complex. These two we don't really need to focus too much on. So we're going to move on because I want to get to irrational numbers. And I think this next one is going to be a little bit better for that. So remember, we have all real numbers. So I've gone ahead and colored this in so we can kind of see what I'm going to be talking about here. And real includes every single one of those except for the imaginary that we talked about in the past. So all of these are a part of the real. So what's left, this green circle that's left, is where the irrational numbers fit in. They are real numbers, but they are not rational. And if you remember what we said, rational numbers have decimals that end or repeat. End or repeat. They're decimals, right? So what do you think irrational means? Well, irrationals are numbers that do not, with decimals that do not end and do not repeat. Okay, so what kind of fractions or decimal, what kind of things make that? Well, you're going to have any kind of number that does not end or repeat. Usually, well, one I can think of off the top of my head that everyone should know is pi. Remember pi 3.1415 and so on. It never, 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 never repeats, and it never ends either. So pi is one. Another one, the common irrational numbers you're going to see are numbers that are inside of a radical sign. And these are things that are not perfect squares. So just because you see a radical sign does not mean that it's an irrational number. What is radical 4? Well, radical 4 is actually 2. So that goes in the natural numbers section, okay? So anything with a radical is not necessarily irrational. If you can take the square root and it's a whole number, it can go in one of these other categories. But if you do square root of 2 and stick that in your calculator, you'll see that it has a decimal point that never ends. And so that means that this is an irrational number. There's plenty of others, square root of 7, square root of 11, all kinds of things. So you will most likely see in irrational numbers, numbers that are under a radical, or numbers that we've given a symbol to, such as pi or Euclid's number. Okay. So now I've got some I've got it written down here for you. So those of you who are like writing better as opposed to pictures, or are taking notes like you're supposed to be, these are some good things to write down in addition to that chart. If you didn't write down the chart showing all the Venn diagram, you rewind, pause, and write it down. But go ahead and pause here and write down these definitions and examples. Okay. Now I've got some practice for you. So number system practice, you're supposed to identify what the smallest number set is for each number that you see here. And then if a number is irrational, be sure to indicate that as well. Because remember, there wasn't an actual number set that indicated an irrational number. Irrational numbers were in the number set of the real numbers. But I do want you to indicate if something is irrational or not. So go ahead and press pause. Do these 8 problems, and then come on back. Welcome back, welcome back. So the number 24, that is a natural number, okay? Negative 12 over 6. Well, I see that's a fraction, so that must be a rational number, right? Well, we can actually simplify that more. Negative 12 over 6 is the same thing as negative 3. So that lets me know I can put it in a smaller set than the rational numbers. It is a rational number, but the smallest set that it can fit into is the integer set. Okay. Square root of 16. Oh, look, a square root, a radical sign. So that must mean it's irrational. Well, nope. Square root of 16 is the same thing as 4, and we know 4 is in the natural number set. 0.25, okay, that's a terminating or ending decimal. So that's going to be in the rational number set. Square root of 7. Well, when I plug that into my calculator, I don't get a pretty number like this without a decimal. I get a decimal that doesn't seem to have an ending. So negative 7 is only the smallest set it can fit into is a real number set. Okay, and these real numbers, this one happens to be irrational. Okay, negative 3, all of my negatives, whole numbers are going to be integers. Okay, 0, remember, that's the only number that's specific to the whole number set only. Pi. Pi, we know because it's a symbol, it should be easy to recognize it as an irregular number. And remember, all irregular numbers fit into the real number set. So that is the smallest set it can fit into is real, and it is an irregular number. So those are your number sets in the number system. We'll see you for the next lesson.